Hello, so can I introduce to you Ignat Korchagin, who will be speaking about live patching, weak crypto, and OpenSSL engines.
Hello. Hi. Everyone can hear me back then? Yeah? So? What about now? Yeah? Fine. Okay, so today we're going to talk about live patching with crypto with OpenSSL engines. Just a disclaimer, most of the talk here are kind of offensive, so like how to crack things. This one is not. This is actually how to fix things, so be prepared. First, a bit about myself. My name is Ignat. I work for Cloudflare. I currently do performance and security. I do a lot of low-level things with Linux kernels, bootloaders, and I enjoy crypto, so hence my talk here. Okay, what does it mean with crypto? Okay, sorry. What does it mean with crypto? How do you define weak crypto versus strong crypto? It's actually very easy. Like, weak crypto is it creates a visible defense for you, but actually if the attacker puts enough effort, they can actually blow away your defenses, right? Versus strong crypto is strong, so no matter how hard the attacker tries, they cannot break into your system. So the question is, like, why people use weak crypto in the first place, right? Well, most of the time I've seen is like developers just don't know what to use. For example, if you look with all the OpenSSL algorithms out there, most new developers, they just get confused. And if you do know that AS is better than DES, then on top of that you have to select the cipher mode, the initial vector, your curve for SEC, and so on. There is also like government regulations. You remember the famous US export crypto in 90s, where they allowed to export algorithms with 40-bit keys, which were crackable even then and definitely now. And finally, the strong crypto becomes weak over time, actually. So some advice you can take away from here is, if you don't want to use, first of all, like, never roll your own crypto. Never do that. Don't copy paste from the internet, Stack Overflow as well. So because they didn't know what to use as well, and also crypto is very sensitive to the environment, so they might have had a different use case. So when you copy paste their code, it will be weak in your scenario. Typical example, any IoT device uses strong IIS with hard-coded key in the firmware image, right? So also, prefer to use high-level cryptographic libraries. Don't focus on algorithms or initial vectors. There are many other libraries out there which give you like use case-based cryptography. Like, I want to encrypt a file, I want to send the data over the network, and they will likely choose all the algorithms and parameters for you to be safe defaults, and they're maintained and reviewed. So why does strong crypto might become weak over time? There is, like, mathematicians just get smarter, right? Strong crypto is based on the fact that there is no efficient algorithms to break them, but sometimes people come up with ideas and they succeed. And also the technology advances as well, so we are all scared about quantum computers, which will probably break everything we know today about crypto. Well, most of the thing. Maybe even cryptocurrency, I don't know. So don't trade too often. Okay, so like the nutshell is, you can't just design a system with strong crypto and use it forever. Over time, because crypto becomes weak over time, you need to do crypto maintenance. You have to throw away the old bad stuff and like put the new stuff in. But it's all good when you maintain your own software, but most of us have to deal with some kind of a software vendors, and sometimes when you see, oh, this software is using obsolete cryptography or any other feature, and you ask vendor to implement it, you usually hit with bumps. So you have the vendor slowness, so they say, yeah, we'll replace the bad crypto in 1 year, and it's not good enough. You have also the abandoned software. There are tons of software out there where companies were acquired, resold, and like they just stopped supporting that. But you still need it for some reason, right? Most proprietary software, you have no source code available to actually modify it. There is also additional cost. Vendor may try to charge you extra to get a stronger crypto. So sometimes they try to sell it as a feature, like SSL companies sell super secure certificates, which are more expensive than the regular ones, right? So sometimes you just can't easily patch your software, but there is still hope. So in this talk, we'll just go through a hypothetical case study that we're fixing a bad crypto in an OpenSSL-based proprietary software. So imagine this scenario, right? You bought some kind, or your company bought some kind of proprietary storage solution. It may be a relational database or an object storage. And the key part is here that it indexes the stored objects via their hash values. And it uses OpenSSL as a crypto backend. Why are we focusing so much on OpenSSL? Because it's kind of a de facto crypto standard nowadays. Or because of its permissive license and popularity, most of both open source and proprietary tools, 90% of them are based on OpenSSL in one way or another, even IoT, Android, and everything. Yeah, so you have all this, and at some point, you invite security audit, and you're like, the auditor, like, what's happened, right? This tool is using SHA-1, so what's SHA-1? Does anyone know what this is? Or doesn't know what this is? So SHA-1 is broken now. SHA-1, which was the founding building block of the internet roughly 2 years ago, is completely broken, and you shouldn't use that. So yeah, you go to your vendor which provided you this database, and well, they usually say it's fine. So that attack described in that paper does not apply to our use case, so you can freely use it. And again, we'll probably replace it in the future in 2 or 5 years release cycle. So who had that in real life? Okay, so and in the end, you have to fix it yourself. To do that, let's take a step back, and before diving in immediately patching the assembly code, we can try to can we do something better here, right? So, and let's reintroduce the concept of shared libraries in the operating system. So imagine you have a process, let's say it's some kind of a privacy VPN client, and you have another process which is a database. By the way, the mascots here they appear accidental, so they do not relate to real life software. And they both need some crypto library, right? And there is a library which is usually OpenSSL, and it says, hey, I have a library. So, and this library is shared between this process. So the nice thing about shared libraries, they are dynamically linked at runtime, so they're not actually, their code is not actually part of your code. They're several entities, and the operating system bundles their code into your code at runtime. And the code is shared between the programs, so you have only one library servicing many applications. The nice thing about it, the code is loaded only once in memory, so even though you have 1,000 processes using OpenSSL, you have only one copy of OpenSSL in your RAM. And it's more manageable. You can update your libraries independently because they're kind of a separate entity. So although our vendor tool is proprietary, let's try to speculate how could a vendor implement this tool. And to simplify it, imagine we have a custom tool from the vendor which calculates a SHA-1 of a file, and this is a simple main function. I will not repeat it again, but the gist here is this: they call this their own implementation of hash file. So they get a file descriptor and pass it to a function. And the first iteration of their hashing implementation might look like this. So they have they just read the whole file in a buffer, which is allocated on a stack. Then they calculate the hash of the buffer, output the result. Simple, right? So we can even check if it works. So we can take this tool, send some data to it, and get the SHA-1. We can actually verify that it actually calculates SHA-1 by comparing the result to a well-known SHA-1 implementation. We can also examine this tool. We can also make sure, because we're trying to fix bad crypto with OpenSSL, that it uses OpenSSL. We can check that which libraries it requires, and we see it's linked to OpenSSL now. Another nice aspect of shared libraries is called lazy binding. So imagine you have a process, and when the process starts, it tells the operating system, I need these two libraries. So what the operating system does for you, it finds these two libraries and loads them into your process address space. But the process does not start using these libraries immediately. It starts executing whatever it needs to do, and at some point later, it needs to calculate the SHA-1, and it tells again to the operating system, hey, I have the SHA-1, and then the operating system asks, like, hey, who has SHA-1 here? And most likely, the typical case, one library has the SHA-1 implementation, and the process can use that code. But the key point here to understand that the list of the libraries the process requires is kind of independent of the list of the functions the process requires. They come from the same place, and usually one function is usually implemented by one library, but that can be changed. And to do that, one of the ways to do that is use the preload environment variable. Who doesn't know what a preload environment variable is? Everyone knows? Yeah, so it basically tells your dynamic linker to load additional libraries into your process address space. And the pre part comes from the fact that this library is loaded before all other libraries the process requires. And this is a typical approach we use to override, modify, tap, or hook like some exported functions from the library. So the way here is some documentation about preload, which is all the. So the way how it works, so basically even before if you have your preload environment variable defined, even before anything happens, your operating system loads your preloaded library into the process address space. And then the usual thing happens where you load the normal libraries. But the interesting part happens when the process now requests a function. The operating system asks who has the function, and now two libraries might have this function implementation, and the process will use the first one which is being loaded, basically our preloaded variant, because it was loaded before everything else. So this way we can basically hook functions into the process. To understand so we're focusing now how to fix bad crypto, so to understand which functions we need to hook, we can analyze our supposedly proprietary tool and see that it requires like two functions from the OpenSSL to do its job. So we can write our hooking library in a way which basically hooks these functions and translates SHA-1 calculations to SHA-256 calculations to make it more secure. So what we do, but we will not re-implement the hash ourselves. What we want is basically we want to reuse the SHA-256 implementation in OpenSSL. So we probably need to resolve the addresses of the same function in the like standard OpenSSL library. This is where we do it. Then, if somebody requested to calculate hash and it's a digest in OpenSSL terms with SHA-1, we basically replace the identifier with SHA-256. We also, in this case, like we'll add our own debugging output to see that, like to observe that our hooking works. And finally, what we need to do, because we're replacing SHA-1 with SHA-256, SHA-1 is 20 bytes, SHA-256 is 32 bytes, and probably the ColonX application might not expect to get the 32 bytes back, so we will actually cut the result of SHA-256 to 20 bytes to comply with the potential interface, right? Yeah, we can compile this code. And now we can call our proprietary tool and preloading our binary, and we will see that we're actually replacing SHA-1 with SHA-256. We can also compare it to a well-known implementation, and you will see now that we're actually calculating SHA-256, but we'll cut it to 20 bytes as expected. So what we did here is we have the proprietary tool, we have OpenSSL, the proprietary tool used that function. We broke this connection and we rerouted it through our preloaded library, which does two things. It replaces the identifier for OpenSSL identifiers from SHA-1 to SHA-256, and it cuts the results to 20 bytes. All good, but if you were attentive enough, or you're sitting in the front row, because probably back rows do not see this, right? Do you see the source code? Good, yeah? There will be a link in the end with all the source available, so you can re-examine later. So basically, if you were attentive enough, you notice that the proprietary tool had a bug. Because it allocated a static buffer, a 4K buffer on the stack, it cannot process files larger than 4 kilobytes. So probably vendor might have noticed that, and they need to fix that bug, right? So they, without changing the interface, they replaced their implementation not to use the static buffer, but to basically use the iterative hash calculation. And OpenSSL API allows you to do that. So you create like an OpenSSL context, you read the file in chunks until you reach the end of the file, and you send these chunks to the OpenSSL context, and it will calculate the hash for you. And then you output the result. But for us, it's a problem. So if we try to run this new updated version with our hooking library, it stops working, right? We don't see our debug output anymore, and we see that it's back to calculating SHA-1. If we examine the updated tool, we see that it now uses different functions from OpenSSL than we already hooked. So we need to rewrite our hook. So again, we resolve the OpenSSL, the addresses of the real OpenSSL functions. We substitute the identifiers to SHA-256. We put our debugging output, and we cut the result to 20 bytes. Compile it again. Now, if we check it, our new hooking library works with the updated vendor application. And we can compare it to the well-known results. Yeah, everything matches now. Good. But the vendor decides to update again. Probably you always hire some smart developers, and some smart developer notice that it's kind of awkward to read from a file from OpenSSL than to send it to OpenSSL context. And like OpenSSL itself has a nice abstraction layer called bio, where can you create like a bio stack, and by reading the file, you immediately calculate its hash. So it's basically, So you create your bio stack. Now you just read from that stack, and it automatically calculates the hash for you. You just get the result in the end and print it. And our fix is broken again. Because if we analyze it, now it uses completely different set of functions, right? So we have to rewrite the fix again. We need to resolve the new functions. We need to replace the identifiers, put our debugging output, and basically cut the result. Compiling, checking, works again. Compared to well-known implementation, also works, right? But this is just a race, right? If you go this approach with every change of the implementation of the proprietary vendor library, you have to rewrite your hooks. You might have to rewrite your hooks, or it somehow breaks your hooks. So the problem is the LD preload approach is very tightly bound to the implementation, not to the interface of the proprietary software. And generally it's the case, but for OpenSSL specifically, we can try to fix it. So like introducing or reintroducing OpenSSL engines. Anyone ever worked with OpenSSL engines here? No? Oh? So actually OpenSSL has extensible architecture called engines. These are extensions modules to OpenSSL, and they basically can be used to add, replace cryptographic algorithms. You mostly work with them if you ever paired OpenSSL with some kind of a hardware device like an HSM or a crypto key. Usually vendors provide an engine-compatible library, so that, for example, you can hook your HSM to Nginx and use it to protect your server TLS private key. And there is a nice tutorial how to build your own engine. So instead of actually hooking the calls between the proprietary application and OpenSSL, we will implement a simple OpenSSL engine called SHA-1 to SHA-256, which will implement in a hash engine is quite easy. You just implement 3 functions, init, update, and final. And our implementation will just call back to standard SHA-256 implementation of OpenSSL, but it will declare itself as a SHA-1 another SHA-1 implementation. Yeah, so we basically implement init, update, and final. We add our debugging output for observability, and we cut the result to 20 bytes. Let's check if it works. So you can compile this engine. You can check it with the standard OpenSSL tool. So here we're calculating the SHA-1, the standard SHA-1 with OpenSSL. We get the real SHA-1. But now we can say to OpenSSL command line tool, hey, can you use our engine for calculation? And now we see that we're actually replacing SHA-1 with SHA-256 and calculating SHA-256. However, it still doesn't work with our custom proprietary tool, because if you do the typical preload, you preload your engine, you won't get anything. It will still calculate SHA-1. And the problem with this approach is because OpenSSL engines are just an API, and to utilize it, calling application have to be aware of these APIs. So some popular applications are aware, as we just saw the OpenSSL command line utility. The OpenVPN, you can set engines. With Nginx, you can set OpenSSL engines. But in general cases, like most applications perceive as OpenSSL as a crypto library, they never care about replacing like implementations of crypto in runtime, so they don't have any code to actually utilize OpenSSL engines. This where we can use another interesting feature when we compile our code, GCC constructor attribute. You can basically mark any function in your code as an init routine, and when you link your code, the linker will put this function into a special constructor list in a final binary. And when if it's an executable when the process starts, or if it's a library when the library is being loaded into memory, basically this code is being automatically executed by the operating system. This is some documentation about the construction. So we can add another function to our engine library called engine preload, or I call it autoload. Here you just add instructions to OpenSSL. So whatever process is running this code should basically use the implementation of SHA-1 as a default for all calls to OpenSSL. Yeah, and the key part here, you just mark your function with the GCC constructor attribute. It's actually not GCC specific. Other compilers have either the same attribute or very attribute with similar functionality, so it's quite cross-platform in that cross-compiler thing. Yeah, I've implemented this function in a separate C file, so now I recompile my engine library with that function. And now when I preload the code, my function gets executed, and it reconfigures the underlying OpenSSL to use my engine as a SHA-1, and even my proprietary tool, which is not engine aware, can benefit from this. And it works now. And now, because we're kind of decoupled hooking from the implementation, we don't care how our proprietary tool, which APIs are used from OpenSSL, we can make sure that the same engine works for every version of our proprietary tool. So we kind of we did it once, and in the end, we kind of say more or less safe from the potential update from the vendor, which will break our hooking library. But there is more. Probably it's very inconvenient not to forget to define the LD preload environment library. And if you somehow miss it, you risk of falling back to weak crypto, and you probably never notice it because all crypto looks random. So actually, you can put this approach further and get rid of LD preload variable. So imagine you have our custom hash vendor executable. All executables, at least on Unix-like system, have a special table called DT needed, where it lists actually all the library it needs to successfully operate. And we see our OpenSSL there. So that's how the operating system knows which libraries to use to load when the process starts, right? So all we have to do is basically add our library to that list. We don't need to recompile any code. In Unix, there is a handy utility for that called patch elf. So basically, we just add our library to that table, to our proprietary custom vendor tool. We can actually verify now the proprietary custom tool depends on our library. Yeah, here it is. And if we just run it without defining anything, we can see we are successfully replacing the SHA-1 implementation, and we don't have to define preloads. So, as a conclusion, I have seen many times when you need to do this sort of thing, or even similar things to change the behavior of some proprietary closed source utility on your platform. People usually, the first thing they think of, we will just decompile it, we'll get straight to assembly. And many times you don't need it. Your operating system provides you with a lot of features and tools to actually influence the behavior on your program. So you're the master of your software. So you can actually, to a very big extent, shift and change the program to your needs without even touching the source code. So these are all the links of all the docs I mentioned in these slides, and the final link is basically the source code I presented here, which is it was stripped down to fit on the screen, but this full source code is available. You can download it, play it yourself, and replay the whole presentation. That's it. Questions? Yes, please. So the question is, although I said we shouldn't roll our own crypto, is it safe to truncate the output of SHA-256 to 20 bytes, as in this example? It's basically a necessary evil. You can probably analyze the proprietary application and try to see if it actually can handle 32 bytes. And if it does, so you can leave it. It's still safer to truncate SHA-256 to 20 bytes than to use SHA-1, because in a perfect world, which SHA-256 is actually not a perfect hash function as well, but ideally a perfect hash function will produce a uniformly distributed output. So basically an attack, if you use a full-size hash from SHA-256, attacker has 2 power 32, has to make up to 2 power 32 guesses to predict the hash, right? If you truncate it to 20 bytes, but assuming it's still good for hash functions are still uniformly distributed, you basically reduce, you increase the attack surface or reduce the security, so the attacker now has to do only power 20 guesses, right? But it's still more secure than the broken SHA-1 function, which has an efficient algorithm to calculate the prey image. Any more? Everyone wants to have lunch. Huh? Okay, thank you.